This conference will now be recorded.
Let's start. So we are going to have a total of 5 sessions related to probability and statistics. In the first 2 sessions, we are going to look at the basics of probability theory. Then we will spend 2 sessions on learning about the various probability distributions which are commonly used in finance and risk management. And then we'll have 1 session on statistics. So that's the outline. As usual, again would want to reiterate that any point of time if something is not clear, feel free to interrupt me and ask about it. Okay, so let's start. The first question, and so majority of you, have you ever done or taken a course in probability statistics, or is this the first time that you would be dealing with these topics? Have most of you or some of you been exposed to this earlier?
For me, it was in 11th or 12th, or in the first year of engineering, but not learned after that.
Okay, okay, okay,
Same for me. First 2 semesters of engineering and prior to that, 11, 12.
okay, okay. So, those of you who already have been exposed to this in the first 2 semesters of engineering, it would be more like a refresher or reiteration of what you would have done there, because uh, the probability that we are going to deal with, essentially, it's more towards applications in risk management and finance, but in terms of concepts, it is typically what you would read in the first couple of semesters in a B school or in a engineering program. So anyways, good. For those of you who haven't been exposed to probability earlier, nothing to worry. We'll be doing this from scratch so that everyone is on the same page. Okay. The first question that may come to my mind is, why do we need to study probability? Anyone, would you like to answer that? Why do you think probability is studied so much in any scientific discipline?
Ability to predict.
Related to?
Ability to predict something, an outcome.
Okay, okay. Ability to predict an outcome. Correct, good. Anyone else?
So
Chance
possibility
of
to
success.
arrive at
Sorry?
yeah, probability of arriving at a result based upon the random variables or outcomes.
Probability of arriving at a result. Okay.
What are the
Anyone else?
likelihood to reach an outcome
Okay,
out of out of several other sample space?
okay, okay. That's using some technical terminology. Correct. Sample space likelihood. Of course, that is there. Anyone else? Okay. See, we study, in my opinion, we study probability so much because no matter what you are doing in life, whichever discipline you are following in life, or even as part of our day to day life, we are faced with uncertainty. That means you don't know how things will evolve in the future, but even though there is uncertainty, we have to make decisions today. So for example, if you are sitting for an exam, no one knows whether they will pass in the exam or not for 100% sure, but you still make plans, you still do things. If someone goes out and walks on the road or they cross a road, there is always a chance, albeit very, very remote, that someone can have an accident, but we still undertake that activity. So the idea is to study probability for decision making and risk management under uncertainty. If there was no uncertainty about the future outcomes, then there would be no requirement of a discipline such as probability theory. So this uncertainty, A, we have to decide. We don't know what will happen in the future, but we still have to decide. And two, this uncertainty can create adverse outcomes. If the future outcome, which is unknown, it goes against me, then I am exposed to a risk. And how do I manage that risk today? That is the part of probability theory. And throughout human history, we've been doing this. So even as an individual, we use probability almost on a daily basis, whether we recognize it or not. We may not be doing it under a mathematical framework, but nevertheless, we are using it. If you see a weather forecast on the TV news and they tell you that there is a 90% chance that it is going to rain today, you will often go out with a raincoat or an umbrella. That 90% chance of a rain that the TV presenter talks about is a statement of probability. If a doctor tells a patient that a particular surgery has a 50-50 chance of being successful or not being successful, that patient actually would be quite worried and they might be looking at also consulting some other doctor, or they might be looking at alternative forms of treatment, because 50-50 chance of the surgery being successful or non-successful is simply not palatable to them. If say Warren Buffett comes on TV and he says that there is a 75% or 80% chance that the stock market will severely decline over the next 90 days, a lot of people are going to start selling stocks in the market and downsizing their portfolios. So the thing is, on a daily basis, we have to make decisions about uh, the weather, our finances, and our health based on these probability statements, which are expressed in terms of percentages. What does that percentage mean? We'll talk about it shortly. Especially when it comes to risk management, probabilities are the fundamental building block of risk management. So wherever you have to, whether you're a weather expert, a weather forecaster, you use probability to provide the percentage that what will be the weather over the next few days. If you are a medical researcher, you use probability to express or to study how effective a new drug is or how effective a new surgical treatment is. If you are a stock market analyst or if you work on a trading desk, mathematicians are hired to apply probability theory for risk management. Okay. Similarly, if you go to the insurance industry, they have a very long tradition of using probability to manage risks. For example, if you want to buy a car insurance, you pay a certain price for that, which is called the premium. The insurance premium that you pay is essentially based on a probability that you will have an accident over the next 12 months. Life insurance, term insurance. As we become older and you purchase a term insurance, it becomes more and more expensive. Why? Because there is a higher probability that compared to someone at 22, someone at 42 may die and the insurance company may have to give a payout. When you take group health insurance, the rates of the group health insurance, they are essentially based on the probability of the amount of claims that the group as a whole will make. So anywhere you go, the idea is anywhere you go where you have to make decision making under uncertainty, whether it is manufacturing, whether it is physics, whether it is any engineering science, whether computer science, whether you have finance, investment, health, construction, wherever you have to make a decision making or risk management under uncertainty, probability is going to be deployed. And of course, when it comes to finance, probability is extensively used in investment analysis, in banking, in corporate finance, and in financial risk management. And that is going to be our focus area, how to use probability theory for financial risk management. Okay. Now, you would also have heard two terms here, probability and statistics. Okay, so I'm sure all of you would have heard that term. So on one hand, you have probability. The other hand is statistics. Typically, the difference is that statistics actually uses probability to make predictions. So, probability essentially is the you can say it is the mathematical theory of estimating the likelihood of something. This is still a pretty vague statement. I will make a more accurate mathematical description, but that can wait for the time being. It is the theory of estimating likelihood of something. Okay. In statistics, what you do is, suppose you want to study some phenomena. Okay. That phenomena is what you call the population. So, for example, from today evening, you will start seeing all these exit polls on TV about the general elections, because the final phase of voting will be over by this evening, and then TV channels can show exit polls. What do they do in exit poll? Essentially, they want to make a prediction about how the entire country has voted and which party will get how many number of seats. The most comprehensive way of doing that is to survey every single guy who is coming out of a polling booth throughout the country and asking for his or her opinion. That is called studying a population. But doing that exercise would be prohibitive in terms of time and cost. And sometimes it may not even be possible. In some scenarios, the entire population will never be available to you as such. So what we instead do is we study a smaller subset, which is called a sample. Okay. And based on the sample properties, so you will measure the sample properties and you will combine this with probability theory to make a guess about how the entire or how that particular property may look like for the entire population. So for example, you may look at the sample mean and combine that with probability theory to make prediction about the mean of the entire population. This is what we call inferential statistics. Inferential because it is being used to draw inferences about some aspect or some property of the entire population. Statistics has another branch which is called descriptive statistics. In descriptive statistics, what we do is we look at the sample or population at hand and we mathematically describe that sample using certain mathematical variables like mean, median, mode, expected value, variance, standard deviation. We try to describe the mathematical properties of the sample as a whole, whereas inferential statistics is that you look at the properties of the sample, combine it with probability theory, and try to make prediction about how the population itself might look like. Okay, this is the major application of probability. Okay, now the simplest way to look at probability is, so probability, as I told you, it's about the theory of estimating the likelihood of something. Okay, now let's talk about certain terminologies. The first terminology is what we call, so whenever you are studying probability of something, what we first need to have is a random phenomenon. That means some phenomenon. It could be a social phenomenon, it could be an economic phenomenon, it could be a natural phenomenon, it could be a physical phenomenon, it could be a thought experiment, whatever the way you want to look at it. It has to be a random phenomenon whose outcome is uncertain. That's why it's called random. Its outcome is uncertain, and you tend to call it as an experiment. Okay, that is the first step. We tend to call it an experiment. Next, in order to apply probability theory, we consider the set of all possible outcomes. So while you may not know which outcome will ultimately happen, but you compile the set of all the possible outcomes. This is what one participant mentioned. This is what we call the sample space, typically denoted by the Greek letter capital omega. So you are studying a random phenomenon which we call experiment. The set of all the possible outcomes of the experiment is called the sample space. This is how it is typically denoted. This is the sample space, and say these are the various outcomes. Okay, then we think of a subset of sample space. Let me say this is a subset of the sample space. This subset of the sample space this is what we call an event A. The subset of the sample space is called an event A. This event, which is a subset of sample space, you can even think of this as a single outcome, in which case the event is a single outcome, or it can have multiple outcomes, more than one outcome. So instead of single outcome, I would say but that is besides the point. The point is, with each of these event A, we want to numerically measure what is the likelihood of the occurrence of event A. So you have a random experiment, a random phenomenon, which you call the experiment. Then you have the set of all the possible outcomes of that experiment that we call a sample space omega. What we are actually interested in is a subset of the sample space, which we called an event A. That is the actual thing that we are interested in, the set of outcomes in which we are interested. And for each such event, I want to numerically measure the likelihood that the event will occur. That is what we call the probability of event A, and this is denoted symbolically as probability of A. This is the beginning of probability theory. And the entire probability theory is actually about these three steps. First, trying to figure out which is the random phenomenon in which we are interested and what are the possible set of outcomes. That means to figure out the sample space, the universe of outcomes that I have to deal with. Then from that universe of outcomes, I somehow want to figure out which is the outcome or set of outcomes in which I am interested. That is my event. And finally, to each such event, for each such event, or to each such event, I want to attach a number which measures the likelihood that the particular event in which I am interested will occur. That number is what I call probability of the event A, PA. Any questions till now?
Yeah, hi. Thank. Just in projects, I usually get to hear that. Can you give us a P10 view of about this project? So does it mean that it's P10, 10% chance of success, or does it mean 90% chance of success? Also, a lot of times they say, okay, can you give a de-risked profile or the de-risked NPV and the risk NPV on a P50 basis or a P20? So I find it pretty confusing at times because are they looking for, say, if they say E20, are they looking for 80% of chance of success and 80% of de-risked value? So if you could explain that, that would be very
First
useful.
of all, what this means depends on how do you define the event. For example, if the event A is defined as success, suppose I have a bond portfolio. Let me get more specific. Suppose I have a portfolio of bonds, okay, and say I pick up a say bond A. If my event is that the event I am interested in is that this bond will default, then the probability that I am going to measure will be the probability of default. On the other hand, if the event is that the bond will not default, then the probability which I am trying to measure is the corresponding probability. Of course, there is going to be a relationship between these two. So I'll shortly come to that. But to answer the first part of your question, whether it is 10% or 90% depends on how you are framing the event. The probability ultimately, the probability is not about something succeeding or something failing. The probability is about that of an event occurring or not occurring. If the event is defined as success of something, then you are measuring the probability of success. If the event is defined as failure of something, it will measure probability of failure. Depends on the context. It actually depends on the context. The second part of your question, uh, I couldn't hear it completely, but what I understood was, especially when you do, in manufacturing or in project finance, they tell you uh, about this P90. For example, in renewable energy, and if I got your context correctly, let me know. Otherwise, you can repeat your question. In renewable energy, you have something called, or in general, a plant load factor. Plant load factor means that if you have put up a certain capacity, say of solar power, how much electricity it will generate. Now, the actual amount of electricity that it will generate is something which is random. No one knows because it will depend upon the weather conditions during the period, how much sunlight that area got, what was the quality of the solar cell that you had used, local weather conditions. There are हजार things. But when you go to, say, a financial institution or a bank to get funding against that, what is the bank's concern? The bank's concern is that, boss, you should be able to pay my debt on time. So while you may not be able to exactly tell them how many units of electricity you will generate a priori, but the bank wants to have a certain level of confidence that at least you will generate this much. You will not, your generation will not go down below this much. Typically, what we talk about that is a P90 PLF. A P90 PLF means plant load factor. That means given a certain rated capacity, how much will it actually generate? A P90 PLF means that this is the PLF. This is the PLF that will be achieved with 90% confidence. This is the basis on which the bank will evaluate your proposal. Of course, there could be a P50 PLF, there could be a P75 PLF, but and you would be intuitively, it would be clear that the amount of electricity that you can generate with 90% confidence is going to be less than the amount of electricity that you can generate with 50% confidence. When you are only 50% confident, then the plant load factor can be much higher, but there is a lesser confidence attached to it. Okay, does that answer your question? Was that what you were trying to ask?
Yeah, it does. So basically, if the bank evaluates the cash flow, and it's say the cash flow, 100% cash flow is say about 100 million. So if they look at a P90 scenario, then that 100 million would actually be 90 million. Is that correct? Based on a
So
P90.
if the rated capacity is 100 million units, if the rated capacity is 100 million units, then the bank would base their proposal on saying that the company will at least, or the plant will at least generate 90 million units. those are the cash flows on which their debt service capacity is being calculated. And the bank will also want to tie the sponsor or the promoter of the project to this P90 number. So if tomorrow the promoter cannot or the company cannot achieve P90, then the bank will typically ask them to partially repay the debt or resize the debt in such a manner that debt serviceability is above a certain threshold.
Thanks, all clear. Thank you.
Okay. Okay. So this is the basic of probability theory. Now the question is, once you have understood what probability theory is all about, the only important question left is, how to calculate this PA. That means, how do I assign probabilities to events? Okay. The simplest way to do this is to assume, or it is the assumption, it's not say even assumption. The simplest reasoning is that the nature of the phenomenon is such that all outcomes are equally likely. This is the simplest way to calculate probability of event. What you're saying is that the sample space has a certain number of outcomes and the nature of the problem is so symmetrical that all the outcomes are equally likely. So for example, you toss a fair coin, there are the sample space omega has two outcomes. You have a head and you have a tail. Okay. Now also think about it. What is the probability of the sample space itself? Anyone, without getting into probability theory at all, what is the probability of the sample space? The sample space is the set of all possible outcomes. Then
One.
what is the say that again?
One.
One
Or
or
100%.
100%. As long
100%.
as you have specified the sample space correctly, it means that whenever the random phenomenon will occur, one of the outcomes of the sample space itself has to happen. That means probability of sample space is 1 or 100%. Okay. Now when it comes to the probability of an event A, A is a subset of the sample space. Okay. Then the relative likelihood of A, this will be a number between
0 to 1.
0 and 1, where 0 means that the event is
Not happening.
impossible, it will not happen, and the 1 means that the event is certain. These are the mathematical bounds on the probability. Either some event is impossible, then you say the relative likelihood is 0, or it is certain 100% it will happen, then that event is having a probability of 1. And I have already shown you such an event. If my event is that something in the sample space will happen, then the probability of such an event, when A is the sample space itself, the way I should have put this is that A is a proper subset of sample space in set theory language. So set theory is something which is very commonly used in describing probability theory. You tend to visualize probability theory or describe probability theory through the language of set. Okay, where you say that sample space is a set of possible outcomes and event is a subset of the sample space. So these are all set notation that we are talking about. Now, in this case, when all the outcomes are equally likely, if I have to ask you to compute the probability of event A, the way you will argue or reason is that let n be equal to total number of outcomes. Let this be equal to total number of outcomes in omega in the denominator, and in the numerator I will have a number like NA, which essentially measures the number of outcomes which are resulting in event A. The ratio of the two is the probability of A. That's what will happen when all outcomes are equally likely. For example, suppose I roll a dice. Now what are the possible what is the sample space? This is omega. Now if the dice is a fair die, that means probability of getting 1 should be equal to probability of getting 2, should be equal to getting the probability of 3, should be equal to getting the probability of 4, should be equal to getting the probability of 5, should be equal to getting the probability of 6, and each of these probabilities is 1 upon 6, because each of them is a single outcome. Each of them is a single outcome, and on the basis of that single outcome, Na will be 1, and n, which is the total number of outcomes in sample space, is 6. So each of them is 1 by 6. Makes sense to everyone?
Yes.
Okay. Okay. This is the simplest scenario. Okay. Wherein you assume that the nature of the problem is such that all the outcomes are equally likely. Such phenomenon would be very, very rare in the real world. These are either theoretical bookish problems or very, very simple phenomenon like tossing a coin or rolling a die. I mean, no matter how perfectly you manufacture a die, or no matter how perfectly you manufacture a coin, you will realize that physically that's all the 6 sides of the die, or all the two or both faces of the coin, they can never be identical. That is impossible physically. Of course, if there is no material difference, you may tend to think that okay, they are all equally likely. That's a fair assumption. Okay, but in general, this is where it stops. For real world phenomena, you cannot assume that the outcomes are equally likely. Okay, so how do you measure? The second approach, which is also known as the classical approach, or we also call it the relative frequency approach. This relative frequency approach to measuring probability was pioneered by a British mathematician, Irving Fisher. The idea here is very simple. The idea is, suppose you want to know, suppose you toss a coin and you are not sure that the coin is fair, and you want to calculate what is the probability of getting head and what is the probability of getting a tail. Say coin is not fair. At least you are not sure about it. Okay, then what will you do? Say I throw the coin or toss the coin 600 times. Okay, and out of these 600 times I get heads 300 times, then I will say that the probability of getting heads is how many times I performed the experiment, which is 600, and how many times I observed my event of interest, which is head. This is very different from the equally likely outcome approach. There, structurally, you had assumed that all are equally likely. Here, it is an empirical approach. You are
But
performing the
actually, it
experiment.
is also equally likely now, na?
Now it is, but that was not inherent in the structure of the problem. So, for example, suppose it so happened that you got the head,
250 times.
yeah, say only 200 times. Then the probability of head would have been 1/3.
1/3.
So in this approach, what happens is, what you measure is the relative frequency of an event. Relative frequency of the event is n, which is number of times experiment was performed okay, and NA number of times A was observed. Okay. Now you will find that as you start performing the experiment, this ratio will keep changing. It will not be a static ratio. If you perform the experiment 10 times, the ratio will be something else. If you perform the experiment 100 times, the ratio will be something else. If you perform the state experiment 1000 times, the ratio will be something else. So what we say is, if we perform this experiment a very large number of times, say n is a very large number, and if this experiment, if this ratio converges to some number k, then that number k is what we call the probability of the event. So in the relative frequency or the classical approach or the empirical approach, when you talk about the probability of an event, what it actually means mathematically is that if I get to perform this experiment or repeat this experiment under identical circumstances a very large number of times, then what is the percentage of times where I am going to see this event or observe this event? That is what it is. Okay, this actually was given by Irving Fisher sometimes in, I think in, this is a fairly new construct actually. This is a more like a 19th or 20th century construct, because Irving Fisher himself, if I remember correctly, he Fisher himself lived between 1867 to 1947. This is a fairly 19th 20th century kind of approach, the classical approach or relative frequency approach. Okay, but long before this approach became popular, there was another approach to probability and statistics, and it is becoming very popular again, especially in the age of artificial intelligence and machine learning. It is called the Bayesian approach. Okay, this is named after a Scottish mathematician from Scotland named Thomas Bayes. He lived during the period 1700 to 1761. So at least like 150-60 years old before Irving Fisher he was born.
There is second approach also called the law of large numbers, or that is different.
Law of large numbers is, I would say, slightly different. Okay, I would say slightly different. We'll get to that. Just bear with me for the time being. The difference between the classical approach or the relative frequency approach given by Irving Fisher and the Bayesian approach is the classical approach is based on empirical observations. That means objective information. To compute probability under the classical approach, you need to be able to repeat the experiment a large number of times and then observe what happens each time. What Bayesian approach looked at, it said that probability, even though it is a number or it is a mathematical construct, he said that probability is a subjective assessment. It is a subjective assessment, and he actually used a specific term for this assessment. He called them prior belief. Okay. In fact, you can think about the classical approach as a special case of the Bayesian approach. In what sense? Say the prior belief is such that there is no subjectivity involved and the entire distribution is uniform. That means, say, based on the past belief or past observations, people would believe that there is no subjectivity involved. There is no subjective information at all. Then classical approach, then the Bayesian approach will transform into classical approach. Now, the reason I want to highlight this is, unfortunately, when it comes to finance and risk management, we have become completely dominated by the classical approach to probability and statistics. Classical statistics, again, is rooted in the belief that what matters is observation in the real world, empirical observations. Okay, this may very well be the case for hard sciences. And by hard sciences, I mean those sciences where you can replicate the experiment under laboratory conditions. But when it comes to social sciences, where you cannot replicate the phenomena under laboratory conditions, I think then it becomes very difficult to apply this approach. Okay, to give you another way, another definition of this, if someone is a follower of a classical approach, they will say that the percentage of times something has happened in the past, that also indicates the probability that it will happen in the future. Percentage is actually a probability statement. Okay, but think about it. When you go to a doctor and the doctor tells you that there is a 90% chance that this surgery will be successful, it doesn't mean that he performs the surgery on you 100 times and then out of those 100 times, 90 times the surgery will be successful, 10 times the surgery will fail. What the doctor is actually doing, he has performed that surgery in the past, okay, and it is his professional judgment that based on what he has seen in the past, there is a 90% chance that the surgery will be successful for you. Or when you have a jury in a court, what does the jury do? The jury looks at evidence, and based on that evidence, they have to pronounce whether someone is guilty or not guilty. Essentially, it's a matter of probability. They have to look at the evidence and they are ultimately deciding upon the probability whether the accused has actually committed the crime or not. But it is not a classical probability. It's not that the jury will run the murder scene. Say it's a murder case. It's not the jury is going to run the murder scenario say 100 times and then say, oh, in these 100 times, 90 times you were the murderer, 10 times someone else was the murderer. So 90% is the chance that you have done it. No, it's a subjective opinion based on the weight of the evidence at hand, based on the witnesses, what they are saying, and based on circumstantial and other hard evidence. Similarly, when we talk about finance, a classical guy or a relative frequency approach guy would say that the history is the perfect predictor of the future. Of course, I'm not saying historical data does not have a role to play. It does have a role to play. But it is not the only useful information. And that is why regulators are continuously warning financial institutions that you should not take history as a given in terms of what will happen in the future. And that is the Bayesian approach. In fact, if you think about it, all the trading in the world happens because probability opinions are subjective. Otherwise, the same security, someone thinks it is overvalued, so he sells it. Someone thinks it is undervalued, so he buys it. They all have same information, but their opinions are different. Okay, so even though in this course we will be talking about the classical or the relative frequency approach only, we will be restricting ourselves to that, but it is very important for you to understand that the Bayesian approach has its own relevance, especially when you when you try to model phenomena which may not be very common. So for example, uh, during the great financial crisis of 2007-8 or 2007 to 2009, a lot of these Wall Street firms, they created all kinds of exotic instruments, mortgage-backed securities, CDOs, credit default swaps. See, when you create a model, how do you ultimately validate that model? By doing something called backtesting. So you have a model and you go back and you test that model on historical data, and then you try to figure out whether you can believe in that model or not. Of course, even if you might have backtested, even then history is not a predictor of the future, because it's entirely possible that the way the market was structured in the past, in terms of technology, in terms of regulations, in terms of integration of capital markets, in terms of the behavior of people at large, in all those terms the market might have changed. So for example, till 2 3 years ago, in a country like India, the movement of the benchmark index was very much determined by the behavior of the foreign institutional investors, or FIIs. If the FII was buying, so FII was kind of the price setter, driver of the price. If they are buying, market is going up. If the FIIs are selling, market is bound to collapse, and collapse big time. Look at what is happening in Indian markets today. There is so much of domestic money which is finding its way into the stock market, and so much of increasing retail participation, that there are extended periods during which the FII keeps selling heavily, and still the market does not fall by more than 2 3%. The behavior has changed. So that is one phenomenon. The other phenomena is, even if the behavior has not changed, how do you backtest it? So for example, during the financial crisis, people found that there were some models which talked about certain events which might affect their portfolios, and they said that the probability of the event was, say, something like 1 in a billion. That means out of 10 to the power 9 trading days, this event would happen in one day. Okay, let me just give you what does a billion actually mean. We tend to think of a billion as 10 to the power 9. Okay, think about it in more hardcore physical terms, and then you can probably appreciate what it actually is. So for example, just open my Excel sheet. Say in a single day you have 24 hours, each hour has 60 minutes, each minute has 60 seconds. This is the number of seconds in a day. Okay, the number of seconds in a year would be 365. Okay, or yeah, number of seconds in a year would be 365. 10 to the power 9. Okay, this is like, to give you that perspective, 10 to the power 9 is approximately the number of seconds in 31 years of your life. But look at it in terms of days alone. 10 to the power 9. How many years of financial data we have available? Even in a country like US, where they have been, they keep data, numerical data very much intact. You have data available for not more than 150 years, or say 200 years. How many days are there how many trading days are there in 200 years? Even if it is 200 years and you assume 250 trading days, this is 250 multiplied by 200. You have data for 50,000 trading days. And I'm not talking about granular data. And we are talking about an event which will happen in 1 in a billion years. Is there any way of backtesting it? There is not. There is no way of backtesting it. So that is the moral of the story. So these are the three different approaches to probability. Now what we are saying is the general mathematical way to describe probability is that there is a sample space which is the set of all possible outcomes. You have an event A, which is this. For every event A, we define a number PA, which is the relative likelihood of event A. Now, because this is a number, and I told you that there is also a belief that there is also an approach which says that probabilities are nothing but subjective beliefs. But even when we talk about numbers in terms of those subjective beliefs, that those numbers should be such that they are in line with intuition. The numbers cannot go haywire. So what we say is that there are certain mathematical theorems, not mathematical theorems exactly, there are certain mathematical rules that this number has to follow. What those mathematical rules are? The first mathematical rule is that this number has to be between 0 and 1. Probability cannot be a negative number, and probability cannot go beyond 1 or 100%, because 100% means the event is bound to happen. Number one. Next, we say that if A and B are mutually exclusive events, what we are only trying to say here is that the notion of probability should be aligned to common sense or to intuition of what actually happens in the real world. Mutually exclusive event means that A and B can't happen together. That means if you know that A has happened, then you know for sure that B wouldn't have happened, and vice versa. So if there are two events which are mutually exclusive, then the probability of A or B, the probability that either A or B happens, is given by the sum of the two probabilities. This is the second mathematical rule which is in line with intuition. If there are, so for example, let's take the case of a die. The sample space is 1, 2, 3, 4, 5, 6. Okay. Now probability of each of them is 1 by 6. Now what is the probability of getting 1 or getting 3? Now these are mutually exclusive. If 1 has happened, then 3 cannot happen. If 3 can happen, then 1 cannot happen. Then the probability of getting 1 or 3 is this. Okay. The reason we talk about this is because in real life, let me bring this down. While we are talking about events, okay, many a times besides individual events, so we might be interested in when we describe the phenomenon or when we describe the set of outcomes that we are interested in, either we are talking about individual events or we may be talking about combination of events. A lot of times we are interested in combination of events. Now see, the individual event is very straightforward. So this, for example, was the event A. Okay. Now typically when you think about combination of events, there are two types of combinations that we think about. One is the event A intersection B, which means we are interested in the joint event that both A and B happen. How would you typically denote this? Through a visually, through a Venn diagram. If this is my omega, this is my A, and this is my B. Okay, then if this is A and this is B, then the set of outcomes this is A intersection B. This is the set of outcomes that both A and B are happening together. Okay, that is one. The other common event that we are interested in is that either A or B occur. In the language of set theory, this is what we call A union B. Now what happens with A union B is if this is A and this is B, okay, then A union B means either A happen or B happens, or you have to allow for the possibility that both of them can happen. So A union B is the entire shaded area. A union B is the entire shaded area. Now, with that background in mind, let us look at the three rules. So the first rule was probability the number between 0 to 1. If A and B are mutually exclusive, that means they cannot happen together, then A or B is probability of A or plus B. And the third is, in general, where they may not necessarily be mutually exclusive, the probability that either A or B happens, this is given as probability of A plus probability of B okay, probability of A plus probability of B minus probability of A intersection B. Okay, this should be intuitively obvious to you. What we are trying to prove is that probability of A union B is probability of A plus probability of B minus probability of A intersection B. Think of this in an empirical sense. PA, if the sample space has n outcomes, then PA is the number of outcomes which are in event A divided by n. Similarly, PB is the number of outcomes which are in event number B by n. Now, if you look at this visually, then what happens? Now look, think about this. The A union B will be the number of outcomes in the shaded zone divided by n, where n is the size of the sample space. Okay, so this is the size of omega. Now here A union B means number of points in the shaded zone. Now if you think about it, when you take probability of A, you count all the points which are lying in A. When you take probability of B, you count all the points which are lying in B. But in this counting, this part, which is common to both A and B, that is getting double counted. To remove the impact of that double counting, you have to remove the number of outcomes which lie in A intersection B. That is why this formula comes. Clear to everyone? Hello?
Yes.
Okay. Now, so these are the rules that we have to follow. Any methodology that you use to ascribe probability should follow these rules. That probability has to be a number between 0 and 1. For mutually exclusive events, probability of A or B is sum of their probabilities, and in general, probability of A union B is this formula. The second formula can actually be derived from that. Suppose if A and B are disjoint, if A and B, where does that formula come from? If A and B are mutually exclusive, how do you denote it visually? This is A, this is B. They are mutually exclusive, so they don't have any common points at all, which clearly means that if we have to find the probability that A or B happens, then that will be probability of A plus probability of B. Looking at it, if you have to find probability of A or B, then either you have to essentially count these points and these points. There is no overlap, so the sum of those points is the probability of A or B. That is why it is probability of A plus probability of B. Or in the union formula, if they are mutually exclusive also means that A intersection B is what we call a null set. It's an empty set. It does not have any elements. If a subset does not have any outcome, then what is the probability of that subset? It's an impossible event, so the probability will be 0. This is another way to express the fact that A and B are mutually exclusive. Mutually exclusive is also known as disjoint. They cannot happen together. So there are multiple ways to express the same thing. A intersection B is a null set, or you can say the probability of A intersection B is 0. It's an impossible event, or the probability of A or B is PA plus PB. All these are different ways to talk about the same thing. Then for every event A, you have an event called the complement of A. Complement is not A. So if A means that A is happening, then complement A means A is not happening. Now think about this. If this is the sample space, this is A, then the entire outer area is A complement. Now clearly, what happens with A and A complement is A and A complement are they disjoint or mutually exclusive? Anyone?
Exclusive, mutually exclusive.
Or disjoint?
I
Because
prefer the word mutually exclusive. This.
yeah, okay. So disjoint or mutually exclusive. Why? Because if A has happened, then the event that A has not happened cannot occur, and vice versa. So they are disjoint, which means the probability of A union A complement will be probability of A plus probability of A complement minus probability of A intersection A complement. This number is 0. So this is this. But there's another way to think of this. A and A complement together, they also become the entire sample space. isn't it? A
Yes,
and A
correct.
complement taken together, they form the entire sample space. And what is the probability of the sample space? It is 1.
1.
This tells you that the probability of the complement event is nothing but 1 minus the probability of A itself. That is one way to look at it. Or probability of A is 1 minus probability of the complement event.
Yeah, just one question. So, in simple language, a complement means that the event is not going to occur, right?
Yeah, it's the negation of the event.
Got it. Got it.
Okay. There's another term that you will often read in probability theory, which we saw here also. It's called events which are exhaustive. Exhaustive means if there are two events A and B such that their union encompasses the entire sample space, then we say that A and B are exhaustive, meaning A and B taken together, they account for the entire sample space. So you will realize here A and A complement, they are not only mutually exclusive, they are also exhaustive. That means they exhaust the entire sample space. Okay, clear to everyone till now? Any questions with this? Anything that you did not understand till now? The basic idea behind probability. Is that clear to everyone?
Yes, sir.
Yes, yes.
Okay. We talked about all the things. Okay, great. So, I mean, when we come, so what I will do is today I'll talk about a certain set of concepts. Then we'll take a break. When we come back, we will try to do some questions around them. So don't worry, we'll also do some questions. See, till now we have spoken of the two events A and B in standalone terms. Okay, that means you talk about the event A, you talk about the event B on their own. A lot of times in real life, what will happen is we tend to think of an event. Suppose I ask you, what will happen to the stock market next year? Or the question is, will or what is the probability? This is a probabilistic question. Will the stock market rise or fall next year? There are two ways to approach this problem. One way is you will say that, look, I have 100 years of data, and in those 100 years, 70 out of those 100 years, the stock market actually rose. That means, based on historical data, there is a 70% chance that next year also the stock market will rise. This is what we call unconditional probability. It means you simply looked at the event and looked at the relative occurrence of the event in past, and whatever the relative frequency was, you ascribed it as probability going further also. But someone else might say that look, I understand that while the stock market rose 70 out of the 100 years in the past, but you also have to figure out that there were 30 years in which the stock market fell down. So the way to answer this question is whether the stock market will rise or fall next year. Look at it in the context of the current environment. That context could be macroeconomic context, geopolitical context, whatever context is there. But you will say that if you ask me this question of whether something will happen or not, I am going to answer that question not in an unconditional sense, but based on context. Context is based on information. The point I am trying to make is if you are appearing for an exam and I ask you what is the probability that you will pass the exam, one way to answer the question is that look, right from the nursery till now, I have given so many exams. These are the number of exams that I passed. These are the number of exams that I failed. You compute the ratio, and that is the probability that I will pass any exam. The more nuanced way to look at this is realizing that all the exams are not the same, and the probability that you will pass a particular exam or not pass a particular exam not only depends on how you have done in the past, but also in the sense of what is the difficulty level of this exam, what is your preparation, how many hours have you put in this exam. That means there is a context which helps you answer this question in a better manner, and that is what we call conditional probability. In fact, you may not realize, but whenever we are answering any probability related question, unknowingly, we are already always making, most of the times, we are making a conditional probability statement. If I ask you, will the market rise or fall? If I check with 10 analysts, each of them might give a different answer because their answer is conditioned upon their analysis and upon their intuition or their judgment. That is what conditional probability is all about. In mathematical terms, what we are saying is, suppose there are events A and B. And say you have already told me that event B has happened. Does this change the probability of event A, or does it make a difference as to what the probability of A is? A lot of times it does. A lot of times it does. So for example, if I tell you that I have studied very hard for this exam, now tell me what is the probability that I will pass. That will be a different probability. But if I tell you I have done nothing for this exam, tell me what is the probability I will pass. It will be a different probability. So we talk about conditional probability. Probability of A conditioned upon event B. That means you know that event B has happened. Now tell me what is the probability that event A will happen. So this was the event A. Unconditional probability is when we talk about event A alone. Conditional probability is when we talk about the probability of event based on some other context. So probability of A given B would mean, now think about it, from a Venn diagram perspective, say this was the entire sample space, say this is A, and say this is B. Okay. When you talk about the probability of A, you are counting the number of outcomes which are in A divided by the number of outcomes which are in the entire sample space. But when you talk about probability of A given B, you already know that B has happened. That means now your sample space is not the entire sample space omega. It is only the number of outcomes which are in B. That is your sample space because you know B has happened. Out of those B elements, those elements where A also happens is A intersection B. If you know B has happened, and now in that context, if you have to say that what is the chance that A will also happen, you will simply say, boss, denominator will be number of outcomes of B because that is my sample space now, and numerator will be those outcomes where A also happens because B I know has already happened. Divide both by number of outcomes in omega, and what you will get is probability of A intersection B by probability of B. The only constraint here is PB can't be 0. B cannot be an impossible event because if B is an impossible event, then how can you condition the occurrence of an event A upon an impossible event B? That is the only catch. Clear? Okay. This is what we call conditional probability. Now suppose it so happens that and conditional means you will say that A and B are, this is a conditional probability, and then you will say that A and B are dependent events. Dependent does not mean that one is causing the other. What it only means is that knowledge about B happening or not happening gives you additional insights into A happening or not happening. So for example, if I tell you that, for example, okay, say in a bond portfolio, you talk about the probability of default. Default alone. This is unconditional probability of default. It doesn't take into account what is the current market scenario. But as any bank or financial institution will tell you that the probability has a lot to do with the macroeconomy. The probability of default during a recession, this is a conditional probability. And you know that when the economy is going through a boom, default comes down, probability of default comes down in those years. Why? Because everyone is doing good, banks have a higher risk appetite to lend, refinancing is easily available, corporate performance is good, so probability of default gets depressed. But during recession, probability of default goes high. Okay. Now suppose A and B are such. The other extreme could be, say A is the event that stock market goes up, and B is the event it will rain today. Suppose you know that it will rain today or it's already raining outside. Does it give you any additional insight into whether the stock market will go up or down? Anyone? Provided it is raining, if I tell you it is raining today, does it give you any additional insight into whether the stock market will go up or down? Anyone?
No, nothing at all.
It doesn't. What we are
No.
trying to say here is that the conditional probability of A, that means the probability of A with the knowledge that it is raining, is same as the unconditional probability of A. That means knowing or not knowing about B does not tell me anything additional about A. Such, in this scenario, you say that A and B are independent. Independent means knowing about B does not tell me anything about A. Or equivalently, you can say, if A and B are independent, then knowing about A tells B tells you nothing about A, and similarly, knowing about A tells you nothing about B. So if I tell you the stock market has gone up today, does it tell you anything about whether it will rain today or not? No. Okay. Or now you know that the probability of A given B is probability of A intersection B by probability of B. Now this is equal to probability of A, which implies for independent events A intersection B is probability of A times probability of B. These are all three different ways of depicting the same scenario. This is also known as the multiplication rule of probability. That knowledge about A gives me no knowledge about B. And remember, if the knowledge that B has happened tells me nothing about A, then the knowledge that B has not happened also tells me nothing about it. Which is like saying if A and B are independent, then in this entire formula, everywhere where you have A or B, you can substitute it with their complement. Then A and B complement are also independent. If I tell you B has happened and that tells you nothing extra about A, then if I tell you that B has not happened, that also tells you nothing extra about A. So wherever in this formula you have A or B, you can substitute it by A complement or B complement and the formula will remain the same. These are called independent events. Now, tell me something. If A and B are mutually exclusive, are they independent or dependent?
Independent.
Independent.
Why do you say so?
One does not affect the other.
No.
Either of the event
Remember the,
happens.
remember the definition of independence. If I tell you about B, that gives you nothing more about A. But if A and B are mutually exclusive, that means that probability of the joint event is zero,
Zero.
which means if I tell you that B has happened, you know for sure that A cannot happen. That means the knowledge about B happening. The knowledge about B happening gives you extra insight about the knowledge of A. So in this case, if A and B are mutually exclusive, then probability of A given B, it has to be zero. They are not independent.
Mhm.
The definition of independence is probability of A given B, which is the conditional probability, should be same as the unconditional probability. This is not the same as probability of A. That is why they are not independent. This is a common fallacy that we tend to think that mutually exclusive means independent. No, it does not mean they are independent. Mutually exclusive typically means they are part of the same physical process or same conceptual process. That is why only one of the outcomes can be achieved. Independence means they are essentially they are originating from different physical processes, and therefore what is happening in one physical process has no bearing on what is happening in the other physical process.
Could you give us an example of an independent event?
I give you the example: stock market going up and it will rain today.
Okay. Thank you.
They are independent events. Okay. Think about what would be possible mutually exclusive events. Just think about them. So, for example, what are mutually exclusive?
Coin toss.
Any
Tossing of
guesses?
a coin.
Hmm?
Tossing of a coin.
But that is too elementary a phenomenon. Think about something, something
Stock
deeper.
market can either rise or fall.
Sir,
Yeah.
one example
Yes.
can
Good.
be, for example, a cricket match. After cricket match, so the celebration or the that ceremony which occurs to celebrate the winning team, because they will be dependent on each other, but
True.
not.
That could be one. Or as someone said, stock market going up or stock market going down. Let me put this in a more numerical format. Say the return from an investment R. Okay. Return R. Consider two different outcomes. In one case, the return is more than 10%. That means your gain is more than 10%. Set of all those outcomes where the return is more than 10%, and set of all those outcomes where you have a loss of 10% or more. These are mutually exclusive, isn't it? No outcome which results in a gain of more than 10% can simultaneously result in a loss of more than 10%, isn't it? Clear to you?
Yes, it is clear.
Okay. Hmm. Let us do. Okay. This is one. Okay. Uh, in general, I told you this was exhaustive. Why did I come here? Let's take this first. Come from. Just a sec. This is there. Okay. Now it's all right. So this was about mutually exclusive. Okay. Then, okay. Now I already told you that in general for two events A and B, I told you about the multi. Okay, this is not the multi. I think I made a. This is a wrong thing. This is not the multiplication rule exactly. So I made a wrong statement there. The point is, in general, for two events A and B, probability of A given B is probability of A intersection B by probability of PB. So you do a cross multiplication. This tells you that probability of A intersection B is probability of B multiplied by probability of A given B. This is what we call the multiplication rule, or alternatively you can say this can also be written as probability of A times B given A, because the other way to look at this is probability of A intersection probability of B given A would be again probability of B intersection A divided by probability of A, and B intersection A is same as A intersection B. So again do a cross multiplication, PA into PB by A or PB into PA by B. And if A and B are independent, Then anyone, what happens to the conditional probability?
Zero.
The conditional probability by definition is same as the unconditional probability. It is 1, or you can say that the conditional probability of B given A is same as the unconditional probability of B, which implies that for independent events the multiplication rule becomes the probability of the joint event is the product of their individual probabilities. This is how you express independent events. These are two different ways to express independent events. Either you say that the conditional probability is same as the unconditional probability, or you say that the probability of their joint occurrence is same as the product of their individual likelihoods. Okay, this is conditional probability. There are two more concepts that we will look at, then we'll take a break, and then when we come back, we will start doing questions around this. Okay. So you thought about, now you know about conditional probability, you know about independent events. Okay, that is done. There is something called total probability rule. The total probability theorem is about, you want to find the probability of something, unconditional probability of something, but that unconditional probability, see, typically what happens is when you collect data or even otherwise, a lot of times computing the conditional probability may be much simpler than computing the unconditional probability. So what the total probability theorem does, it tries to give you some kind of a linkage between computation of one from the other. The way the theorem goes is, say this is a sample space omega. Okay, this omega has been partitioned into 4 parts: C1, C2, C3, and C4. When you talk about probability theory, the word partition has a very specific meaning. So when you say that I have created, so you create partitions of omega. You partition omega into different subsets, but to qualify for that partition means that partitions of omega are such that they are mutually exclusive. That means the partitions do not overlap with each other, and at the same time they have to cover the entire sample space. That means they are exhaustive. They exhaust the sample space. It's a set of, it's a group, or it's a group of non-overlapping subsets which cover the entire sample space. That is what we call the partition. Okay. Now suppose this is an event A. Okay. Then what I can do is, A can be thought of as A intersection C1 union A intersection C2 union A intersection C3 union A intersection C4. That means the set A can be thought of as the union of individual intersection. A intersection C1 is this, A intersection C2 is this, A intersection C3 is this, and of course A intersection C4 is this, and A intersection C3 is this. Now all these are also non-overlapping, and you know that when two subsets are when two sets are non-overlapping, that means they are mutually exclusive, then what happens to the probability of their union? The probability of their union is same as the sum of the individual probabilities. That is what the mutually exclusive property is all about. That means probability of A can be thought of as A intersection C1 plus the probability of A intersection C2 plus the probability of A intersection C3 plus the probability of A intersection C4, and by the multiplication rule, A intersection C1 is probability of C1 times probability of A given C1 plus probability of C2 times A given C2 plus probability of C3 times A given C3 plus probability of C4 times A given C4. A lot of problems that you will get in exams or even otherwise, this is how you have to approach the problem. So they will give you conditional probability, so that means they will give you various conditional probabilities, and from that they will ask you to compute the unconditional probability of the event A. That is what happens in this. This is called the total probability theorem. So in 10 minutes more, we'll just talk about one more thing, and then we'll take a break, and then when we come back, probably we'll spend at least an hour trying to solve problems. And I will relate each of those problems to what we have studied. And by the time you leave the session, you will have a fairly good understanding of what we are doing here. And finally, we have a very, very important theorem in probability theory called the Bayes theorem. This is about the same Thomas Bayes. See, when you think about conditional probabilities, there could be two conditional probabilities, A conditioned on B and B conditioned on A. When I simply express it in this form, you might think that they should be equally easy to compute. If you can compute A given B, you can also compute B given A. In real life, it so happens one of these, in real life, it may so happen that one of these will be very, very difficult to compute. I'll give you an example later. One of these will be very, very difficult to compute, while the other one can still be computed. So what Bayes theorem does, it gives you a theoretical framework, a mathematical framework of expressing one conditional probability in terms of the other conditional probability. How does it do that? Think about it. Suppose you want to compute A given B. Then A given B by definition of conditional probability is A intersection B by probability of B. Now From the multiplication rule, now A intersection B can also be written as B intersection A. Okay, and this can be expressed as probability of A times probability of B given A. See what we have done? This is the relationship between the two conditional probabilities. Probability of A given B is P times A by P times B times probability of B given A. That means the Bayes rule is, or Bayes theorem is, that A given B is B given A times PA by PB. Very, very useful rule. This helps you do a lot of computations. Okay. These are the basic rules of probability that you need to be aware about. What probability is, the different approaches to probability, the equally likely outcome approach, the classical approach, which is the relative frequency approach, then the various rules. How do you combine events using intersection and union, complement, mutually exclusive, exhaustive, finally conditional, unconditional. Then you have independent event. How do you express that? And then total probability theorem, again very, very useful theorem. And finally you have the Bayes rule or Bayes theorem. Okay. Clear to everyone till now? Any questions? I'll be happy to answer, and then we can take a break, and when we come back we'll start solving questions. Anything that you did not understand, or where you think that the explanation was not clear, tell me. Yeah, please tell me. Anything conceptually which was not clear. Yep. No questions from anyone? Can you explain Bayes theorem without annotation? Sorry, what does that mean? Ujjwal, I did not understand that part. Hello? Yeah, Ujjwal. Easy way. I think the easiest way I can explain it, Ujjwal, is that Bayes theorem essentially provides a connection. So the way I would put this is that given any two events A and B, you can create two conditional probabilities. One is A conditioned upon B, and the other is B conditioned upon A. What Bayes theorem does, it provides a link between the two. It provides a mathematical link between the two. And this is the formula. I mean, unfortunately, the annotation needs to be there because it is actually a mathematical rule. So I cannot express that mathematical rule without a formula. Does it answer your question, Ujjwal? Okay. Yeah. Sabuj Kash Chatterjee and Shalu, you want to say something? Please tell me. Hello? Yeah, tell me, tell me. No questions? Concept of A or B not clear. Okay. Fair point. So the point I was trying to make was that we not only talk about individual events in terms of their probabilities, we also sometimes want to combine events. These are what we call, so in the language of set theory, these are called compound events. Events which have been created from simpler events. You know, it's about talking about a richer event or a more complex event, but that how that complex event is getting expressed as a combination of simpler events. So, for example, uh, how shall I put it? Mm, say you have a portfolio of two stocks, A and B. A may rise, B may rise, both may rise, one may fall, both may fall. All these possibilities are there. But from a return perspective, what really bothers you is the portfolio return. Okay. Now your portfolio return may be decent provided A rises by a substantial amount or B rises by a substantial amount or say both A and B rise by a substantial amount. So what you might say is, what is the probability that A goes up by 10% or B goes up by 10%? When you make this statement in English language, what it means is the event which is of interest to you is you are happy if A goes up by 10% or B goes up by 10% or both go up by 10%. That means A or B. This is the meaning of A or B. In the set theory notation, the event is A union B. A union B means either A happens or B happens or both happen. That is either or statement. Either this happens or that happens. A or B. Let me put out the word either, that might be confusing to you. So this is what we mean by A or B, A union B. A lot of times what you are interested in is both have to happen together. That is your concern. A and B together. When you say that, now the event we are interested in is A intersection B. Then you might be interested in the event that A does not happen. That is the complement of A. Okay, and you can extend this to more than two events. So if there are three events, A, B, C, you can talk about the joint event A intersection B intersection C. That means all of them happen together. And you might also talk about their union, A union B union C. That means either A or B or C, or A and B, or B and C, or A and C, or all of them happening together. This, the way you will depict this instead in Venn diagram is, this entire shaded area this is A union B union C. Does it answer your question, Shalu? Is it clear now? Great. So now let's take a break. I think we have done a lot of concepts. It's now time to practice questions around that. So how much time do you all propose for a break?
Sir, half an hour.
Okay, half an hour.
This conference will now be recorded.
Now let's start doing some questions. Also, when I do these questions, I just want to make an additional remark. See, one thing is to talk about an event A, just as a symbol. But when it comes to finance, a lot of times what we are actually interested in is some numerical variable. The event that we are interested in the discipline of finance and risk management essentially are numerical variables. Say the return from an investment, risk in a portfolio, loss, gain. We are always interested in that. So when I do the questions, we might do some questions on generic events also, but more often than not, the way I will talk about an event is, say, set of all the outcomes where say R is more than 5%. This is an event. This is the standard notation for an event. In curly bracket, it means set where the outcomes are defined by this statement. And the best way to write the probability, the theoretically correct way is this, but because the notation becomes too much to write, so typically books will write it like this. But when you see probability of R being more than 5%, it means the probability of the event whose outcomes are such that they result in the variable R exceeding 5% or more. That is that just keep that thing in mind. Okay. Now, with that, let us do some questions. I actually wanted to write some questions. I have written some questions on a piece of paper. So, two hedge funds. Okay. Alpha. So what I'll do is, I have the questions actually written with me on a piece of paper. So when I circulate this session notes, I will write the questions in detail, but think about them right now. Two hedge funds, Alpha and Omega. Okay. Let me mark this as a question so that I can write it later. Two hedge funds, Alpha and Omega. Probability that the fund Alpha generates positive return. That means return from Alpha is more than 0 in any given year is, say, 60% or 0.6. Similarly, the probability that the fund Omega gives positive return in any given year is, say, 70%, and R alpha, that means the return from fund alpha and the return from fund Omega, they are independent. Based on this, what is the probability that both the funds generate positive return in a given year? It's important to look at the notation which I am writing, because that's how you actually solve questions. Okay, now tell me, what is the probability that both of them are positive, given that the two returns are independent? Now you know that when two events are independent, if A and B are independent, when what happens? Remember, if A and B are
Probability of
independent,
A into
then
B.
probability of their, wait, where did this go? When A and B are independent, the joint probability is the product of the individual probabilities. This will be 0.6 multiplied by 0.7, which is 0.42, 42%. Okay. What is the probability that in the same year both funds are in losses? What do you think about this? How do you depict this event? If fund omega alpha is in loss, that means R alpha is negative. If omega is in loss, that means R omega is negative, and we are saying both are loss making, so that is the intersection event. Now tell me, if their returns are independent, then the fact that they are losing money are also independent, right or wrong?
Yes, sir.
Okay, so you can say that this is equivalent to probability of R alpha losing money times probability of omega losing money. Now they have given you the probability of alpha making money. Now tell me, what is the probability of alpha losing money in terms of this probability?
Balance.
Remember,
0.4.
probability of A
0.4.
complement, sorry,
0.4.
correct. So in the probability notation, this is 1 minus the probability of R alpha being positive. Okay, and similarly, this is 1 minus the probability of R omega being positive. So as you said, 1 minus 0.6 times 1 minus 0.7. Clear to everyone?
Yes, sir.
Okay, let's do another question. There is a corporation ABC. They have issued bonds. These bonds are rated triple B. Okay, probability that the bonds get upgraded within a year is 8%. Probability of a downgrade is 4%. What is the probability that there is no change in rating over the course of a year? the important thing is structure this solution in terms of how you would argue for a probability. So what we are saying is that this rating is something which is uncertain. Currently it is triple B, but what it will be after 1 year is uncertain. But there are only three possible outcomes. Either it is upgraded, or the rating is downgraded, or there is no change. Think of
I
each
think
as
these
an
are
event.
mutually exclusive, so just add the probabilities.
Absolutely correct. Absolutely correct. These are mutually exclusive because only one of them can happen. So probability of upgrade plus probability of downgrade plus probability of no change, that will be equal to how much?
Uno.
1. So now you know this implies probability of 1 minus 8% minus 4%, which is equal to 88%. Okay, clear to everyone? Let's do another question. Suppose there is a stock XYZ. Say the probability that the return of this stock, the loss, will be 10% or more is say 20%. Okay. Also, the probability that the return will be more than 10% positive return, this is 30%. Then what is the probability that XYZ either, I'm giving this to you in English, either loses more than 10% or gains more than 10%. This means the probability of either or. How do you put it in set notation? Probability of
Union.
R.
Union.
A
Very
union
good.
B.
Very good. R being less than minus 10%, union R being more than plus 10%. Now what kind of events these two are?
There are also
Mutually
exclusive
exclusive.
Mutually exclusive. So for mutually exclusive events, for the either or problem, what is the probability?
PA plus PB.
Absolutely correct. Which is 20% plus 30%. Clear to everyone?
Yes, sir.
Let's do another problem. I will quickly type this for you. The problem says 30% chance that oil prices will increase, okay, over next 6 months. 30% chance of that. Also, if oil prices increase, then there is a 60% chance that stock market will go down. Okay. What is the probability that oil prices increase and just read the language of the question, and stock market is down over the next 6 months? This is the question. First of all, what are the events? The first event is that
Stock market going down.
The first event is oil price going up. Okay. Let me write this like this. Probability that oil price will go up is 0.3. Look at the second statement. If oil price increases, then there is a 60% chance that market will go down. What kind of a probability that is?
Conditional. P/A/B.
Excellent. So probability
stock going down / oil increase.
That the stock market goes down conditional on oil going up is 60%. Now what the question is asking is, what kind of a probability they are asking now? Joint probability. They are asking you the probability of the event that oil goes up intersection
stock price going down.
Stock market goes down. Now you already know that for any two events in general, probability of A intersection B is probability of A multiplied by B given.
B.
You know that?
Given, yes.
This is probability of A. This is the multiplication rule. If you apply that rule here, then this will be probability of oil going up times probability of conditional on oil going up. So this will be 0.3 Understood?
Yes, sir.
Okay. A lot of times, doing these probability questions, how shall I put it? I think. Okay. Next. Okay. Now let's do another question. Suppose there are two bonds. Okay. Two bonds. Both have probability of default 30%. Okay. They are really like B-rated bonds or something like that. 30% probability of default, but Their default probabilities are statistically independent. Now there are a set of questions. Probability that both bonds default, probability that only one bond defaults, and probability that neither bond defaults. Let's think about this. Okay, let's say there are two events. So you have event A is that bond A defaults, and I have event B that bond B defaults. The problem tells you that probability of A defaulting is same as probability of B defaulting, which is 0.3, but their default are statistically independent. What does it mean by that? What do you mean by their bonds are statistically independent?
It means that like the probability of B when A has happened is actually equal to probability of B. It is not affected by happening of,
Or
or you can just say PBA into
if I
PB
tell
gives the
you that
combined.
if I tell you that one of the bonds has defaulted, it does not give you any additional information about
About
default
the,
or non-default of the other bond. Okay?
yes, yes.
So
Go ahead.
probability that both of them default is the event A intersection B, where A is A defaults and B is B defaults.
0.3
Because
into
they are in 9%, you agree? Clear to everyone?
Yes, sir.
Okay. What is the probability that only one of the bond defaults? Now think about how you will frame this particular statement in probabilistic terms. What is the probability that
First we
only
will
one bond
assume like A will default and B won't default, and other B will default and A won't default, and then add those both.
that means A intersection B complement, A
Yes.
defaults and B doesn't default,
Plus
or
A
A
complement
doesn't
into,
default and B defaults,
yes,
which will be like now because A and B are independent, so A and B complement are also independent.
0.3 into 0.6 plus 0.6 into 0.3.
B complement
0.7, sorry, 0.7.
this will be probability of A defaulting times 1 minus probability of B defaulting plus probability of B defaulting, which will be zero point 0.3 into 0.7 plus again okay, clear? And finally, probability that none of the bond defaults. That means event is A complement intersection B complement, which is probability of A complement times probability of B complement, which is 1 minus the probability of A times 1 minus the probability of B, which will be 0.7 times 0.7 is 0.49 or 49%. Did all of you understand this part? Is this clear to everyone? Tell me. Clear to everyone?
Yes, sir.
Yes.
Yes, sir.
Just a sec here. What happened? A very intuitive way, another way to argue about this problem was that you started with two bonds. AB, and you will say that look, qualitatively only three things can happen. None default, only one of them default, or both of them default. These are also events. And what kind of events these are? These events are
Mutually exclusive.
mutually exclusive. Excellent. And they are not only mutually exclusive, they are also exhaustive, because these are the only three possibilities that can happen. They cover the entire sample space, which tells you that probability of none of them defaulting plus the probability that one bond defaults plus this has to be equal to 1. And you can see that the way we computed it, this one came to 9%, this one came to 42%, and this one came to 49%. Here, look, 9%, 42 and 49, the sum total is 100%. So part C, actually we might not even have computed, or part B. If we were able to compute part A and part C, we could have simply said about part B, 1 minus 9% minus 49% 42%. That is another way to argue about the entire thing. Clear? Okay, let's do a slightly more, I would say, a difficult problem, or not exactly a difficult problem, a more involved problem. Problem says your firm forecasts that there is 50% chance of market going up significantly next year. Significantly being up, 20% chance of significantly going down, and by design 30% chance that market will be flat. That means neither substantially up or neither substantially down. Now you have to figure out the prospects of a new portfolio manager. You have to figure out a new portfolio manager. This manager has a long bias. That means he's someone who is a perennial bull and is likely to do better in a bull market. Okay? Based on past data, you believe, how the manager has performed in the bull and the bear market, you believe that there is 80% chance that this manager will be up. That means his portfolio will be up if markets are significantly up, and there is a 10% chance that this manager will be up if the markets are significantly down. Okay? If markets are flat, manager has an equal or 50-50 chance. Manager is just as likely to be up as to be down. What is the unconditional probability that the manager will be up next year? Read it carefully, and then we will try to solve it. Let's read it. Look at the problem first. It's not a straightforward problem. Okay? Did you all read the problem?
Yes, sir.
Yes, sir.
Now, think about this problem. Suppose we denote the market performance by M and the manager performance by, say, X. What is the information that the problem already provides you? First, the problem tells you that the probability of market being up 0.5,
0.5, down 0.2, and 0.3.
market being down 0.2, and probability of flat. Also, it tells you this manager has a long bias. That means he is likely to do better in a bull market. And what is that? Now, which kind of probability we are talking about? We are talking about conditional or unconditional in the second half of the problem.
Conditional.
Conditional.
So it says that the
Probability of
probability
manager X dependent
being
market
up when the market is up. This is
0.8.
0.8.
80%.
Probability that the manager is up in a bear market. This is only
0.1.
10%.
10%.
And probability that he will be up, this is 50-50. And what you have to find out is what is the probability that this manager will be
Up.
giving an up performance. Now, this kind of problems, you have to find an unconditional probability, but what you are given are a set of conditional probabilities.
Conditional data. Yes.
You
This
can
is
use
where
that
you
Bayes theorem. No?
no, this is not Bayes. In Bayes, you have one conditional probability getting expressed in terms of the other. Here you have to find a linkage.
So can't we use like probability of X up, conditional M up into probability of X up is equal
I
to
tell you,
probability of
I tell you,
this?
I tell you, I tell you. See, what will happen is, think about it. Here, a tree-like structure will be very, very useful. See, suppose this is the market. Okay, the market has only three things to do. So this is market being up, market being flat, and market being down. The question tells you the probabilities of these as 0.5, 0.3, and 0.2. Okay. Now, given each of these scenarios, there are two things that the manager can do. Given the market is up, manager can either be up or manager can be down. Similarly, given that the market is flat, manager can be up or manager can be down. And similarly, given the market is down, manager can be up or manager can be down. You agree?
Yes, yes.
Yes, sir.
Now the problem says the first it gives the probability of this one. This probability is actually probability of the manager being up, but on which branch? When the market is up. Okay. So think about it. If I ask you what is the probability that the manager actually goes up, his portfolio does well, gains, and you will say that look, this is like saying, now think about it. Wait. Look at this point where the manager is up. This is the probability that the market was up and the manager was also up. Correct? Isn't it?
Yes, sir.
Similarly, this is the probability that the market was flat, but the manager was up. Okay, and here also let me, I think I made the wrong notation here. This point is the probability that market was up. And finally here you have the joint probability that the market was down, so you can say that the actual unconditional probability that the manager is up can be broken down into three
Add these
mutually
three.
exclusive events. This, this, and finally this. Can we say that?
Yes, sir.
Okay. And these events are what kind of events? They are mutually exclusive. Only one of them can happen, na?
Correct.
And now you know how to use the multiplication rule. The first probability, the joint probability, can be written as probability that market is up times the probability that the manager is up when the market is up, plus the probability that the market is flat times the probability that manager is up when market is flat, and finally probability of market being down times probability of manager being up. Even though market is down. Now you can see this is 0.5 times 0.8 plus the next one is 0.3 times 0.5 plus 0.2 into 0.1. So this is 40% plus 15%, which is 55% plus 2%. Clear? You saw how we solve these problems? What we did, this was an application of the total probability theorem. So what we did, we first identified the base events, market being up, flat, down, and on those base events, we conditioned the event that we were interested in. Clear to everyone? Hmm?
Yeah, clear.
Okay. Next. So these are typically, a lot of times you will find problems like this when they will give you a set of conditional probabilities and you have to compute the unconditional probability. Okay. Now think about it here. Calculating the unconditional probability of manager directly was difficult, but you knew the performance of the manager in different market environments, and based on that you computed the overall probability. Okay. Now Let's do another problem. Say probability that GDP decreases is 20%. Okay. Probability that unemployment increases is say 10%. And you also have probability that unemployment probability that unemployment increases given that GDP has decreased is 40%. Then what is the probability that GDP decreases given that unemployment has increased? Look at the question. What it tells you is, first of all, let's figure out what the statement tells us. It tells you that the probability of GDP going down is 0.2. Probability that unemployment goes up is 0.10, 10%. And it also tells you the probability. Now we are talking about a conditional or unconditional, the third one.
Conditional, sir.
Anyone? So this is the conditional probability that unemployment increases given that GDP has declined, that is 40%. And what it is asking you is, what is the probability that the GDP has declined given unemployment has increased? This is the application of what concept? You have one
Reversing
conditional
the
probability.
conditional probability.
This is
Bayes
the
theorem.
application of Bayes theorem.
Yes, sir.
According to Bayes theorem, probability of A given B, remember what did we look here? Probability of A given B was probability of B given A into PAPB. Or the same token, you can say the probability of B given A was the probability of A given B times PB by PA. Both ways you can write it. So in this case, the conditional probability that the GDP has declined given the unemployment has increased can be expressed as the other conditional probability where unemployment increased while GDP declined times probability of GDP going down unemployment going up. Okay, and if you do this, it will come to the first conditional probability is 40%, GDP going down 20%, unemployment going down up 10%. This is a very thought-provoking question. Look at the two unconditional probabilities. If I told you that the GDP has gone down, then the probability that the unemployment has also gone up is only 40%. But if I tell you that unemployment has gone up, then the chance that the GDP has gone down is like 80%. Look at the asymmetry of the situation. What this tells you is that in scenarios where GDP is going down, the country is going into a recession, unemployment may still be prevented by things like government action. A very good example is the Work for Food program in India, that Rural Employment Guarantee Act in India, Manrega. So even if the GDP is going down, probably the government can engage people and engage them in activities, and unemployment may still be retained. But if you know that the unemployment has gone up, then probably there is a very high chance that GDP would have declined. But again, it is only 80%. There is a clear situation where even though GDP might have gone up, unemployment may also have gone up. Agreed? If you look at the first conditional probability, what will be its complement event? The complement event will be probability of unemployment going down
Unemployment, GDP up.
given GDP going down. Now that is the complement event. If you have the conditional probability A given B, then one complement is A complement given B. Okay, this complement event will be 1 minus 0.4. That means there is a 60% chance. There is a 60% chance that if the GDP has gone down, then unemployment has also gone down, as per this problem. On the other hand, if you look at the complement event of this one, conditioned on unemployment going up, there is only a 20% chance that the GDP would have gone up. That is the asymmetry. That's what Bayes' theorem is able to highlight. Okay, we'll do one more problem on Bayes' theorem. This will be a very interesting problem, practical application, and then we will move on to another topic. Now look at this problem very, very carefully. Let me write it down first. Your institution has a model for forecasting bond defaults. Okay, model is 90% accurate. What this means is, of the bonds that actually default, model identifies them correctly 90% of the times. Similarly, of the bonds that do not default, model correctly identifies 90% of them. Okay? So you have a portfolio of bonds. Okay? Each bond has 5% probability of default Here's the interesting part. Given that the model predicts that a bond will default, what is the probability that it actually defaults? Did you all understand the question? This is how you actually deploy models within an institution. So you create a model. Now when you deploy the model, what do you do before deploying that model? There's an activity that you do. Can anyone tell me what is that?
Train and test.
What test?
Train the model.
Train the model. What do you do in training the model?
Feeding the data and
You are doing what
already
we back testing. That means how good the model is in predicting past events. That means you will calibrate the model, then you will actually feed the characteristic of each bond into the model and ask the model based on historical, actually on actual what has happened in the past, you are asking whether this bond will default or not. And you are saying that the model is 90. That means when you back test the model, once you have trained the model on the data, you back test it. The back testing results are 90% accurate. That means of all the models, of all the bonds that the model said would default, 90% of them actually defaulted. And of all the bonds that the model said did not default, based on historical training data, 90% were such that they actually did not default. That means model was 90% accurate. You got this part? So what is 90% here? 90% here, if you ask me in terms of probabilistic languages, probability that the model said a bond will default given, now you're back testing, you know what actually happened in the past. Given that the actual was a default, that is 0.9. And this is also the probability where the model said that the bank would not default given you knew that in actual there was no default. Sounds like a great model, 90% accurate. And this is a problem which is very, very relevant in prediction and machine learning both, because machine learning ultimately is about predicting. You have to realize that a model might be very well trained on past data, but actually what you are bothered about is how good the model's predictions are on data which is real world. That means on which the model has not been trained or which the model has not seen in the past. This problem actually highlights that difference. What actually it is asking you to do is, it says the accuracy is all fine, but suppose the model says, now the conditional probability is inverted. Suppose the model said something will default. What is the probability that actual will be a default? These are two very, very different probabilities. And you will be surprised to find that even though in one direction that conditional probability was 90%, but let us try to figure out how that probability will be in the other direction. Now by Bayes rule, this can be written as probability of model being D, given actual being D, multiplied by probability of actual being D divided by clear to everyone till now? Are we on the same page? You all understand this is just the Bayes rule formula?
Yes, sir.
Now, see this probability, the first probability is fairly easy. It is given that this is 90%. The second probability is also fairly okay. This is only 0.05. Each bond has a 5% probability of default. The problematic part is the denominator. What is the probability that the model says it will default? Now think about it. There is a bond. What can happen with the bond? The bond can either default or no default. It means the actual event is default or the actual event is non-default. Now when you train the bond model on this data, for the bonds which actually defaulted, there are two options. Either the model correctly predicts default or the model incorrectly predicts non-default. Okay. Similarly, on the set of bonds which actually did not default, the model might be incorrect in saying that it will default, or the model might be correct in saying it will not default. Okay. Now the scenarios where the model will actually predict default can be broken down into two components. The first component is where the actual is default, and given that the actual is a default, the model says that yes, there will be a default. That is the first scenario where the model says that there will be a default. Okay, this is one scenario. Just give me a sec. Where actual is default and model also says there will be a default, and there will be an alternative scenario when actual is not default, but the model being model, it can also give incorrect results. But the model says it will default even though actual was non-default. Okay. Did you understand how I wrote this?
Yes, sir.
Now look at this. What is the actual probability of default? 0.05. The second one is actually the accuracy of the model. That given that there was a default, model also said there was a default, and we all know that the accuracy is 90%.
90%.
Second one is probability that the actual there was no default, that is 95%, because this is the complement event. Think about it. Probability of actual not being a default, probability of actual not being a default is 1 minus the probability of actual being equal to default, correct? Which is 1 minus 5%, which is 95%. So this is 95, not defaulting. Now, even though it did not default, the model incorrectly predicted that it will default. This is what? This is the inaccuracy of the model. Now you already know that the model is 90% accurate. Then what is the inaccuracy of the model? 10% by
0.10.
definition. So you do this. This is 0.045, correct? And plus 0.095. This is coming as how much? 95 and 45, 140.140. Okay. Now you do the number crunching. This will be
There is some issue at my end. You other guys are also facing it?
Yes, we are not able to hear.
I think I got booted out for a couple of minutes. Can you all hear me?
Yes, we can hear you.
And
Yes,
can
sir.
you see my screen?
Yes, we can see.
Okay, great. So where were we? We were talking about the model. This was 0.95. This was 1 minus probability of actual being default. That is 1 minus 0.05, which is 0.95. And this is the inaccuracy of the model. So I think the number we had worked was 0.140. And now you have 0.9 times 0.05 divided by 0.14. And the answer is 0.3214. Doesn't it sound strange? A model which was 90% accurate on historical data, but if you work on that model's prediction, what that model is predicting will actually crystallize in the real world is only 32%. Why do you think that is happening? Intuitively, why do you think that is happening?
Overfitting.
Can anyone tell me why do you think that is happening?
Maybe some other behavioral reasons.
Hmm? Hmm. Yeah, the behavioral reasons which lead in a bond default, they were there in the past data also. But mathematically, why do you think that is a problem? The problem, anyone, would you want to take a try? Why do you think this is happening? Okay, this is happening. This is a very, very usual scenario where the event that you are trying to model itself is a rare event. Think about it. The actual default event was only a 5% probability event. The actual events of default are fairly rare in the world. They do not occur often. That is why when you train or calibrate a model on data, past data, which actually had rare occurrences of that event, and when you use that model to make a prediction, the fact that it will actually happen like that drastically goes down. Mathematically, if you ask me, the problem is that the model was trained on a data set where the occurrence of that particular event, see that the event that you are actually trying to model is the default event, but the occurrence of that event itself was very rare in any data set. That is the actual problem. If you do machine learning, this is called a scenario where, so you are trying to do this is like solving a classification problem. I give you an input and you have to classify it in one of the two buckets, default or non-default. Now when you train, what is happening is this training data set is highly what we call imbalanced. Imbalanced means in machine learning you will learn that these train the training exercise will work fairly well when both the buckets in which you are trying to classify the event or input, they are equally balanced. That is supposed to be the best scenario. But here in the training data set, 95% of the data, if the training data set was randomly chosen, if it was a good training data set, then the characteristic of the universe would percolate into that training data set as well. That means 95% of the data points in that training data set would show no default, and only 5% would say default. And when you train a model on such a data set, this is what happens. Okay, any questions? Nothing? Did all of you understand this problem? How this problem evolved? What was the challenge in this problem? Did all of you understand? Did you find it counterintuitive? Yeah, please tell me. This is a key feature of probability. The challenge that people in general have with probability is a lot of probability modeling is fairly counterintuitive. That is why you need the notation so that you are on the right track. Otherwise, it would seem very counterintuitive to you that a model which is 90% accurate on historical data in terms of the actual accuracy of its predictions in the real world is only 32% accurate. Which means no matter how well trained your model is on the historical data set, especially if it is modeling a rare event like default, fraud transactions, any prediction that it makes, you have to take it with a pinch of salt. Okay? Any questions till now? Did you all understand at least now how to work with problems involving total probability, conditional probability, independent events, mutually exclusive, A intersection B, A union B, complement, Bayes rule? Is this clear to everyone?
Yes, sir.
Okay, great. So if this is clear, then let's start talking about the concept of random variables. As I told you, we have been talking about sample space, events, probabilities of events, but most often, especially in finance and risk management, majority of the times, what we are concerned about or what we are interested in is some numerical variable. Now we will start only talking about in terms of numerical variables. So numerical variables whose values are uncertain. The other word books sometimes use is stochastic. Stochastic means something which cannot be predicted a priori. You don't know it in advance what it will be. The So numerical variables whose values are uncertain or stochastic, they are called random variables. There is uncertainty about the value that the variable can take. Okay. The opposite of random variable is something called a deterministic variable. What happens with deterministic variable is if I tell you what it is now, you can tell me what it will be in the future. For example, we all learnt in school physics that if you drop a body from rest and you neglect air resistance, then the distance that it covers is given by half gt square, where g is the acceleration due to gravity and t is the time elapsed. Here s is a completely deterministic variable. If I tell you what the value of time, you will just punch it in the formula and give me what the value of s will be. That is the deterministic variable. Okay. Now, this is a random variable and the value that it actually takes is called a realization. So realization is the outcome or the So realization means, wait, the way it is happening is, let me talk about it in a bit more detail. So you have a sample space, but what you are saying is that, look, now I am not interested in the event A as such in terms of the outcomes of the event A. What I have done is, to each such outcome I have mapped a number x. That number is what you call a random variable, because the event itself is probabilistic. So if every event is getting mapped to a number, or every outcome is getting mapped to a number, then that number is also random. For different events, the mapping will result in different numbers. Okay, so instead of saying the probability of the event A, what you will actually say is, what is the probability of x taking a certain value. So instead of saying probability of event A or the outcome, we are saying what is the probability of the random variable taking a value k. Okay, now the entire sample space. So think about this. When we say the sample space is the set of all the possible outcomes, so what will happen is, in this sample space, all the outcomes have been mapped to a number. That means you can think of the sample space, forget about the sample space the way we were talking about it earlier. Now my sample space is the set of values that this random variable can take. Okay, and to each such value you can assign a probability that is now the complete probabilistic description of the experiment. Did you all understand this part? A random variable is nothing but, whatever we have studied about probability till now, what we are saying is, we are interested in a numerical variable, not in some general subjective events. So to every event we map a number. That is what we will talk about now. The sample space, instead of the sample space, we will say, what is the sample space? Since every outcome of sample space is mapped to a numerical variable, it means the sample space itself is the set, can be thought of as the set of all the possible values that that numerical random variable can take. And the particular value that it takes is called a realization of the random variable. And you define probability for that. It's very simple. Earlier I was telling you, if you want to understand a random phenomena, think of all the possible outcomes that are possible, and then assign probability to all the possible events. If you do it, you have a complete understanding of the random phenomena. Here what we are saying is, think of the random phenomena as a set of numerical values that can manifest themselves, and then assign probabilities to each such outcome, and now again you have a complete description of the random phenomena. Okay, now because this is a numerical variable, now numerical variables are of two types. One, what we call discrete. So you have a discrete random variable, and then numerical variables are continuous. So you have a continuous random variable. Discrete random variables are those which can be counted. For example, number of defaults in a portfolio. This is a discrete random variable. Continuous random variable are those which are measured. Things like returns. It's a continuous random variable. Gain, loss, these are all continuous random variables. Okay. Now the question is how. So going forward, stop thinking in terms of sample space and event. Just think in terms of a random variable. Let's look at the first one. Which is a discrete random variable. How do you work with a discrete random variable x? For a discrete random variable, how do we describe the phenomena using a discrete random variable? We have something called a probability mass function. For a discrete random variable, we define a PMF. What does the PMF tell you? The PMF gives you the probability for each value that the random variable can take. That's what PMF is. Suppose the random variable can take one of the three possible values x1, x2, x3, then the PMF means a function which tells you what is the probability of x being equal to x1, say this is p1, what is the probability of x being equal to x2, say this is p2, and what is the probability of x being equal to x3, say this is p3. In general, if it can take I different values, then the PMF is telling you what is the probability that x takes the discrete value xi, which is pi. Because each of these values is a probability, that means each pi will be a number between 0 and 1. That is one thing. And if the random variable takes values x1, x2 up till xi, and so these are the only possible values that the random variable can take. That means if you take a sum of these probabilities, now think about it. Also, in the world of random variables, if I define an event x equal to x1, what does this mean? This means a set of all the possible outcomes that result in the random variable x taking value x1. And I consider another event x equal to x2. Now, based upon whatever we have studied till now, can you tell me what kind of events these are? They are what kind of events?
Discrete events.
Sorry? They are?
Mutually
Mutually
exclusive.
exclusive.
Exactly. The reason they are mutually exclusive is because if this was my sample space and these are the set of outcomes in the sample space, then what is the random variable doing? Each outcome is getting mapped to a separate value. A single outcome can only be mapped to a single numerical value. A single outcome cannot result in two numerical values. That means each outcome, the set of all the possible outcomes which result in a particular random value of the random variable, they are distinct from the set of all the possible outcomes which result in a different value of the random variable. So this and this are mutually exclusive, which tells you that if I take the sum of these probabilities, that means the probability that x equal to x1 plus this will be equal to 1, because that is the entire sample space. Over the entire sample space, the random variable is taking values from x1, x2, x3 up till xi. That means the sum of those probabilities has to be equal to 1. This is what you call the PMF. Now, typically, how the PMF will look like for a discrete random variable. For a discrete random variable, how do you think the PMF will look like? For each of the possible values that the random variable can take, you will have a point probability. On the x-axis, you have the values that the random variable can take, and on the y-axis, you have the probability of k. This is how the PMF looks like. Okay. A common example could be that, say, x takes values -3, -2, -1, 0, 1, 2, 3, and then you have a PMF which says, so this is 0.05, 0.1, 0.2, 0.3, then again 0.2, 0.1, and 0.05. You got this? It's not looking very great. Wait. The way we are depicting the PMF is the value of x and the PMF is x, taking that value x. So this is -3, so this is 0.05, -2, 0.1, -1, 0.2, 0, 0.3, 1, 0.2, 2, 0.1 and 3. This is how the PMF looks like. For all the possible values that the random variable can take, it will assign a probability value. Now tell me something. If I ask you what is the probability of x equal to 4, what do you think it will be? Anyone?
Zero.
0, because the random variable does not take that value at all. But if I ask you what is the probability that the discrete random variable will be, say, the discrete random variable is less than equal to 0. Now, to solve a problem like this, you will say that I have to add up the probabilities of all the individual points which satisfy this criteria. That means this is the probability of x being equal to -3 plus the probability of x being equal to -2 plus the probability of x being equal to -1 plus the probability of x being equal to 0, which is 0.65. So for all the value that the random variable doesn't take, the point probability is 0. But by using the less than equal to statement or greater than equal to statement, you can argue about other kind of events. For example, if I ask you what is the probability that x is either less than equal to -2 or x is greater than equal to +2, then what will you say? X greater than equal to less than equal to -2 is like saying that x either takes -3 or takes -2. That probability is 0.15. Similarly, x being greater than equal to +2 means either x takes 2 or takes 3. That is also 0.15. And these two are mutually exclusive. So you take a plus sign and the answer is 0.3. Understood, everyone? Did you all get this part? Tell me, tell me.
Yes. Yes, sir.
Okay. Now, a lot of times, see, when it comes to random variables in general, so for a discrete random variable, you can do two things. Either I can ask you for a point probability. That means what is the probability that the random variable takes a particular value? Either it will be 0 if the random variable does not take that value, or it will be, you can read it from the PMF. The other probability that we are very often interested in is the probability that x is a value less than equal to some x. This has a very specific name. It is called the cumulative distribution function. This is called the cumulative distribution function or CDF of a random variable. So for a discrete random variable, one function is what you call the PMF, which gives you the point probability. The other important function is what we call the CDF. How do you think the CDF will work? For example, if I take this one, let me take this example itself. How do you think a CDF of this will look like? The PDF should be fairly obvious to you. Let me, what we can do is, let me take this page. This is the PMF. Now, if I ask you to draw the PMF, how will you draw the PMF? Say this is 0.05, say this is 0.1, this is 0.2, and this is 0.3. And the values that it take are -3, -2, -1, 0, 1, 2, and 3. So the way the PMF will be drawn, at -3, the point probability is this. At -2, the point probability is this. At -1, the point probability is this. At 0, the point probability is this. At 1, the point probability is again this. At 2, the point probability is this. And at 3, the point probability is this. This is the PMF. You can just, connect them. But if I ask you to draw its PDF, CDF, how will it look like? This is the PMF. Now suppose I want to draw the CDF. Okay. And draw the CDF over the entire number line, -infinity to +infinity. What will happen? Till the time you reach -3, the random variable does not exist. So what will happen? Let me plot this. So say -3, -2, -1, 0, 1, 2, and 3, and then it just goes on. How will the CDF look like? Till -3, there is no probability because the random variable does not exist at all. 0. Then suddenly at -3, there is a jump. Till here it was 0. Then suddenly what will happen is there will be a jump of 0.05. Come here. There will be a jump. Now from -3 to -2, again flat because no other probability is there. At -2, it will again accumulate a probability because there is a point probability, again a jump. Again flat. Then at -1, it again accumulates, again a jump, again flat. At 0, it again accumulates, then 0 to 1 flat. At 1, it again accumulates, 1 to 2 flat, again accumulates, 3, and from there it will be this. And what the values will be? The values will be till -3, it was 0, this is the probability. Then at -3, it suddenly jumps and becomes 0.05. Next step is of what amount? 0.1. So now this is 0.15. Next step is another 0.2. So 0.2 plus 0.15, this will be 0.35. Then another 0.3, 0.65. Then you have from 0.65, this is minus 3, minus 2, this is minus 3, minus 2, minus 1 and 0. Then you have 1. I think I've just jumped again. Wait. Minus 3, minus 2. How many points? 1, 2, 1, 2, 3, 4, 5, 6. Okay, I have to give one more. There will be one more here. Jump from. Probably I messed it up. Just a sec. Till minus 3 there was nothing. Then there was a point jump. Then again at minus 2 there was a point jump. Then at minus 1 it became 0.35. So there was a point jump. Then at 0 it became 0.65. Again a jump. At 1 it became 0.85. Then at 2 it became 0.95 and 3 it became 1. This is, and in between it will all be flat. So from here to here it is kind of flat, and again it jumps flat, jumps flat, jumps flat, jumps flat, and finally it like this. This is how the CDF will look like. 0.65, then you had 0.85, finally you had 0.95, and then you had 1, and it will remain at 1. This is how the CDF looks like. One of the defining characteristics of a discrete random variable is that its CDF looks like a staircase. Now if I ask you, what is the probability that the random variable is less than equal to 3? Now all the values that the random variable can take, they all get accumulated. So this is 1. Similarly, I ask you, what is the probability that x is less than equal to 5? All the probabilities will combine. That is why it makes the final jump when x takes the value 3 and then becomes flat at value 0, at value 1. The CDF has reached its ultimate because it's a probability ultimately, it can't exceed 1. But if I ask you, what is the probability that say x lies between 0 and 2 or 0 and 1.5? Anyone? What is the probability that it takes value between 0 and 1.5? Anyone?
CDF at
0.5.
1.5 minus CDF at 0.
This will be the probability that x takes value 0 plus x takes probability 1. 1 point, beyond 1, then it's 2. But it is only talking about 1.5. So this will be 0.2 plus 0.3, which is 0.5. This is how you work with discrete random variables. If I give you the PMF, you can compute the CDF. If I give you the CDF, you can compute the PMF, because the size of the jump at every stair, this jump from 0 to 0.05 is actually the PMF at minus 3. Then from 0.05 it makes a jump of 0.1, that is the PMF at minus 2. From 0.15 it makes a jump of 0.2, that is the PMF at minus 1. This is how you compute. The height of each stair in the staircase is the point probability at that point. Did you all understand this? Hello?
Yes, sir.
Okay. So these are random variables which we can count. Then there are other random variables which we cannot count, which we can only measure. Now the question is how you work with them. They are what we call the continuous random variables. How do you work with them? Suppose there is a continuous random variable x. Now, in case of the discrete random variable, you had a PMF. What did the PMF tell you? The PMF told you the point probabilities for each value that the random variable can take. What was the point probability? When it comes to continuous random variables, a statement like this, that the probability of the continuous random variable taking a value k, this statement itself is meaningless. Or you can say that the point probability is 0. For a continuous random variable, the only logical statements we can make are what is the probability that it lies in a range. You can put a equal to sign here, but that is immaterial. It doesn't matter because point probability has no sense in a continuous world. Reason is, if I tell you that the random variable takes a value 0.32 with some probability, say 0.1. Now what can happen is in a continuous world, because the scale is continuous, whatever measurement you are taking, it appears discrete. Why? Because it is a function of the accuracy of the number of digits that you have chosen. So when you say something is 0.32, what it means is that all the values which were from say 0.316 to 0.325, you can think of the measurement of 0.32 up to 2 significant digits as a rounding off of measurement of up to 3 digits. This is how we round off. That means if this probability was 0.1, then this probability is now distributed over this entire zone. Similarly, if this is 0.316, you can think of this as the 0.316. You can think of this as 0.3156 to point say 3165. That means what you are measuring is actually a continuous scale. You can keep drilling down. You can keep increasing the accuracy of the measurement. That is why on a continuous scale, the statement of point probability is meaningless. You can only talk about the random variable taking values in a range. There is no point about making a statement that the temperature is 30 degree. What you can only say is what is the probability that the temperature lies in the range 29 to 31. Now, how do you define this probability or compute this probability? For the continuous random variable, you have a function fx, which is called the probability density function. Just like you have a PMF, here you have a PDF. The only constraint on fx is that fx cannot be negative for any value of x. Say this is the PDF. Okay, then the probability that the random variable takes values in the range a to b, and this is an linked to the what we did in calculus. It is this area, and this area is given as the integral of the PDF within the range a to b. Of course,
So this
the
looks like cumulative. It looks like CDF,
this is not CDF. This is
but
not
it is
CDF.
in the but it is a cumulative.
This is not cumulative. I'm only talking. I tell you, okay. When it comes to cumulative, what you will do is you will be talking about the probability of x being less. Remember, cumulative is always about this. So for this, how cumulative will happen? You take it from minus infinity to plus infinity, and say this endpoint is P, and say this endpoint is Q. Okay. So what will happen is with the cumulative, this is P and this is Q. Till P, very minimal probability, then cumulative will start rising till Q, and then it will become like this. This is how CDF will look like for a continuous random variable from 0 to 1. This is CDF. The CDF will be like this, a smooth curve which goes from 0 to 1. This is the PDF, and the probability that it lies in a range A to B is given by area under the PDF between the 2 points, so it is the integral. In fact, this, I'll tell you how it compares to, why you got confused probably. This you can think of as the probability that the random variable lies between minus infinity to x. So this you can think as the integral from minus infinity to x. Okay, if the starting point of measurement is the leftmost end minus infinity, from there if you measure till x, this is the CDF. Got the point? And the CDF is always denoted by capital F. Here also. Always capital F. Clear to everyone till now? So we'll stop here today.